it's just an example of how it can push bricks in different environments. Of course, we also put it onto mobile vehicles as well, do some tests on that, so it works really well. The challenge here is the fact that it's actually quite complex mechanism, quite expensive, so you could put it onto mobile vehicles, but it's quite expensive, but it works well. We've shown it works well. So ideally, the next stage is to miniaturize it, make it simpler, cheaper to use, and then try and get it onto vehicles to do things that are interesting. But yes, it works quite well, which is good. I'm going to skip this one, we're a bit short of time, so I'm going to come to this one here. So I'll give you an example of exploration. So far what I've shown you really is all about exploring in, I guess, search and rescue, the built environment. But I mentioned at the beginning that it could have applications into surgery, into medical applications. So we're doing some work exploring the body with small robots. So there's a bit of surgery called laparoscopic surgery. That means basically doing surgery through a very small hole. It's a case of restricted access. You want to go through a very small hole, in this case it's through the skin, and you want to be able to do stuff on the other side to perform surgery, operations, take samples. Ideally you want the fewest possible number of holes in your body, of course you do. So if you have one hole, it can be quite hard to see what's going on. So ideally you have a very good viewpoint. So what they're doing here, they have surgery, you have metal tools that go through, the metal tools can do things, but you want to be able to see very clearly what's going on. So what we were trying to do, we wanted to build a robot that could go inside the body, that could walk around, and could give you different camera images of the surgery that was going on. So here's the question here. So ideally, you want to be away from the surgery. If you were to put a robot in here, it's going to go across all kinds of weird organs. It's very, very hard. But the top of the stomach here, so you put in gas, the gas inflates it. So this point here is actually a pretty good path, a bit curved, but pretty good. So the question is though, if you want to walk upside down, inside the body, on wet tissue, how do you do it? And the wet tissue is just, it's hard to describe, it's slimy, it's really, as you imagine, quite grim. So it's a difficult environment, so how can we do that? So we spent quite a bit of time looking at this, and we took inspiration from the tree frog. The tree frog is adapted to go into forests where it's all wet, it has sticky feet, and can get a good grip. So wouldn't it be great to put one of these things inside your body for surgery? Perhaps not a frog, but a robot version of it would be a good thing to do. So how can you do that? If you look at the frog's feet, it has these micro pillars. These are very, very small patterns on its feet. And what happens is, when it touches wet material, you get what's called a fluid bridge. The liquid sits across two of these pads, you get a void there, and that causes adhesion, causes a sticking force. So we went away and we made these things. I showed you at the very beginning different fabrication techniques. Here we're making things that are incredibly, incredibly small. So we're doing things like light etching. You can't possibly machine it mechanically. It's a very advanced process to make these small dots. If you look on an electron microscope, we'll zoom in. These are real pillars here. We're zooming in. Incredibly, incredibly small things. You can't see them with the naked eye. Very, very small micro pillars. But they're what cause the adhesion. So when you get a cut of these things, you stick it onto wet things, it sticks. Not a lot, but you get about 20 grams per centimetre, but certainly enough to be able to stick a robot on. So we built a robot. This, of course, is not the right scale. It's a big one. You wouldn't inside your body. So we built a robot to do that. It's still kind of a micro robot, though. It has 8 different motors. So inside here is a motor. One motor there, also a motor inside here. So 8 motors in a very small scale. Here it's working on metal for testing. You can see here, these little motors, very, very small. These are 5mm motors, so really micro motors. And you can see, so you can see it can walk around, it can use this technique. Obviously it's too big. But one thing that's quite interesting, if you get a sticky pad and you put it on, if you want to pull it off, by its definition, it's sticky. You put it on, you've got to pull it off. But what you can do, and what the tree frog does, as the tree frog puts its hand on the thing, it twists its hand, effectively it peels its foot off. So if you can, as you pull it off, if you can twist your wrist or your leg, the force drops dramatically. So therefore, you put it on, high force, as you pull it off, you twist, it's easier to get it off. And you'll see here, what's happening here, as it comes off, we're applying a force to twist it, very subtle effect. The back bit comes off first, let me do it again. So it's twisting, and that maybe drops it by, I don't know, 2/3. It's a much, much smaller force. It's quite a nice thing. But you can see here, of course, we're such a long way off making a frog. So it's our best attempt. This was probably about 4 years ago now, 5 years ago now. This was our best attempt. And it really is one of the world's most advanced at the time, 8 motors in a small scale. But we're so far off making the tree frog. So we went away and we thought, oh, how can we try and improve it? So we need manufacturing techniques that can increase complexity. How can I make one of these things that has 300 motors at that size? Obviously, you can't do it now, it's science fiction. How could I do it? How can I make it smaller? How could I have 3D integration? So right now, we have a motor. We put a motor inside a mechanical structure. Wouldn't it be great if the actual motor case was part of the overall structure? That way you're not duplicating things, you can really get the best possible thing. And also, minimal assembly. This was made by a PhD student. It took him weeks with very small pairs of tweezers, assembling things, trying to make things happen. It's just not feasible. You need manufacturing techniques that can make fully assembled working robots in one go. That's what we're trying to do. So we've got a large facility. So actually on the back of this, we wrote a government grant. We've got about a £5 million facility to do that. And it's all about trying to manufacture robots. So manufacturing equipment for robots. You can see here, we've got 3D visualization stuff. Very large machines designed to make very small parts, strangely enough. So very large machines. Large machines have very high spindle speeds. They have very high precision, which means you can make things that are very difficult to make normally. We've got the world's largest 3D printer. It's multi-material, so it can print things that are over 1 meter in square, so really large structures. And you can see here what we're doing. What we're doing here is we're going to laser cut a small dragonfly wing. So we've got a very expensive laser cutter, £500,000. And what it's going to do here is going to cut a very thin bit of material, and we're trying to replicate dragonfly wings for a small flying robot. You can see there we've done it. It's made out of titanium, very high precision, very small micro structures we can cause on that. So for manufacturing, I'm going to give you, we've got about 10 minutes left. I'm not going to overrun, so I'm going to be quite quick on this. I want to give you a flavour of some of the things we're doing in terms of manufacturing these robots. So the first thing is, we're trying to make, I mentioned before, minimal assembly. Can we make a robot that is assembled in one go? What we have here, we have a small walking robot. All these legs here work on this kind of principle here. But we manufacture it in 2 pieces. The bottom part contains all of the legs, all of the joints, pre-assembled. So we print it in one go, then we add 2 motors, we put a top on, it's a walking robot. So it's quite a nice example of actually in situ manufacturing. So I'll show you a video here of what we're doing. So we're printing the structure in one go, we're adding the motors, we screw it together, and it walks. So all of the legs here are pre-assembled. Nobody has put it together, completely pre-assembled, put it together and it works. So it's a good example of see here walking again, of actually making a robot in one go going forward. We're doing lots more advanced 3D printing stuff. So one thing we're trying to do is, you saw before, we print it out, we add the motors, we make it work. Wouldn't it be great to print around motors? So we're doing 3D printing. This is with robot arm here. It's quite simple stuff. It's just an example. So robot arms printing things in different directions. We have a more complicated example here. So what we're doing here is we have a motor, propeller blade, and we're going to print an aeroplane around the motor. You get a motor, propeller blade, and let's print the aircraft around the motor so there is no assembly. So obviously still work to do there. So the challenge there, of course, is that so we can print it absolutely fine. It all works well, integrating the things. But we're making an aircraft structure out of 3D printed materials. We need to have a better aircraft structure than you would do conventionally to do it. So we're working on that right now. So we hopefully quite soon we'll get it working. But I think it's a nice example of things going forward. One thing we're aspiring to do, you saw the little walking robot. We want to go away, we want to make a mechanical structure, a walking lion, and we're calling it the Leonardo's lion. So Leonardo da Vinci designed a lion based upon gears and mechanisms. So rather than trying to do exactly the same design, what we've said is, okay, if he was around now, how would he go about designing this in a more modern way, 3D printing? So we've tried to build a 3D walking robot in one go with no assembly. Designed completely already in CAD. This is a real video of what would happen, so it does work. We want to print all of these different things in situ. So the idea is you print it off, a meter big, you attach a motor, and it walks away. That's our vision. So we've designed it all works. The problem we have is that when we 3D print it, if it doesn't work, it can't be fixed, of course. So we have to be really, really sure that we can print it. So for example, if we print a meter by a meter robot, it costs around about 40,000 UK pounds. So it's very, very expensive. So if we're not careful, we'll print it off, we'll try it, it doesn't work, stick it in the bin. So we have to really, really sure it works. So that's what we're working on right now. Although we could do it now, until we're sure we won't do it. Next year coming up, we're working very much on quadrupeds. So we're going to buy all these commercial quadrupeds. We're going to buy all these. We've already ordered them, in fact. So for next year, we're going to work with this year coming up. Taking a lot of our technology and putting it onto legged robots. This one here, this animal here, state of the art from Sweden. Sorry, and it costs around about 250,000 UK pounds. Very, very expensive, but very, very impressive. These robots here, these are 10,000 UK pounds from China. Not so advanced, but it shows how amazing China is actually at making things at low cost. In 10,000 pounds compared to 250,000 pounds. Slightly bigger, but still. So anyway, so this year coming up, we're going to be working very much in that area, trying to use these leg robots for exploration type tasks. Okay, that's good, so I'm on time. So just in conclusion, so what I've showed you today really is lots of things about robots getting into difficult environments, getting things. And I think one thing to emphasize is it has a really good business case. At the very beginning I mentioned this. It kind of seems like toys, it seems like fun. But commercially there is a really good opportunity for these kind of technologies to make a massive difference, especially in the pipe robot type domain. So I won't talk any more now. Hopefully I've inspired you to think about robotics. I think we'll have about 3 or 4 minutes for any questions you might have. So anyway, thanks for your attention. It's been really good. Thank you.